want to start off by clarifying something that we did last time. We'll make a change, okay? So I don't think this is going to be a hard adjustment, but so I kind of misspoke last time. There. Try again. I want to clarify this notation that I brought up last time. So this R notation, okay, so this R notation, this thing where we said the rate of change of f with respect to x. What we want this to mean is, this is contrary to what I said last time. We want to reserve this notation for the approximate rate of change that's built from the average rates, okay? So that's this notation will be the approximate rate of change built from the average rates. So we should all be able to write, you can quiz yourself, we should all be able to write what that is then. So if that is the approximate rate of change function built from average rates of change, we should all be able to write what that equals. Take a minute to do it. If you can't, then you're not keeping up with us, okay? Because this is what we've been doing the last week or so. Who wants to give it a shot? Nicholas.
Step function?
No, it's not the step function. Chloe. F of x plus h minus f of x. Approximate rate based on average rates. So yes, that would graph as a step function. Yeah, you're right. That would graph as a step function. But we also want to write exactly what it is. Sorry, Nicholas. So yes, this would graph as a step function, but I was asking for the rule. Okay, I was asking for the rule. Okay, now we want to keep in mind that, so is it exact rate of change? Ever?
When h is really small.
When h is really small. So it can represent both. Okay, it can represent both. Okay, it does represent exact range, the rate of change, when h is sufficiently small. Okay, so it does represent. So this notation is kind of versatile for us. You know, if h is some finite value, then it's the average rate of change function, approximate rate of change. If h is small enough, it's the exact. Okay, so hopefully that doesn't upset things too much. Is this okay? So this R notation will just be that ratio, that's the average rate of change function. And we know that that can be exact rate when h is sufficiently small. So going back to where we were last time, what were we doing last time? So now we're building from this open form definition, we're building these closed form rules. Okay, we're building the closed form rules, and we were on this one. So let's just review this slide. You know what to write. So we talked about John's distance after x hours, Mary's distance after x hours. And from the given information, John travels a distance 5 times as much as Mary, and so then we said, well, naturally then, his rate is 5 times Mary's rate, or speed. Okay, so we're again, we're looking at, we know what this means now, and so we have these other notations. So we read all of them as rate of change of f with respect to x is 5 times the rate of change of d with respect to x. But this first one has a slightly different meaning. Okay, these two are exact. They're always exact. So how would we change that ratio to represent these? So that ratio of f of x plus h over h. What we also need then to say precisely the exact rate of change. What do we need? Okay, so if we're saying that RF is RF is f of x plus h minus f of x over h, right? Change in y over change in x, rate of change. And we know that's what that is. How is this different in terms of a rule? So in terms of a rule, how would this be different? Yeah.
The rate of change for f of x with respect to x, that one is actually the process of it, and then the other one is the plug and chug.
It's still the process. What I'm asking is, this is still comes from this average rate ratio, but now this, how do we have to change this rule so that it equals f? Go ahead.
Did you say the limit? Is that what?
He wants the limit. Which limit?
The limit from 0, not from h to 0.
As h approaches 0. Jamal, is that what you're going to say? Yeah, so now these two notations require that we have the limit as h approaches 0 of this ratio. But this one does not. This one does not. So this is our approximate rate, both average rate. It can be the exact rate when h is sufficiently small. But these notations have to be, or are, exact rate of change. So they, if we're going to use this open form to write these notations, we would need to include the limit as h approaches 0. Is it okay? Is that clear? Okay. So we were working on this one. So we said, okay, just from common sense, if the distance is 5 times, the distance of John is 5 times the distance of Mary, then the speed of John is 5 times the speed of Mary, and we were in the middle of that. Okay, so then I should point out, so then Wednesday's video is going to have this, me announcing that r sub f of x, the rate of change of f with respect to x, that notation means exact and has the limit in it. So you need to, we're changing that, okay? So we're changing that. Yeah?
So I just need to clarify. So the r of x with just the f of x plus h minus s, that is the approximate rate, and it does not require the limit, the little notation of limit.
Right.
But the other two are considered exact, so they do require the limit.
Perfect.
Okay, I just wanted to clarify.
Perfect. Yep, you said it perfectly. Yeah, Marco.
Does d over dx mean like the rate?
Yes, so, yes, thank you. So it's another notation meaning the rate of change of f with respect to x. So the rate of change of f, so with respect to x. And so you can kind of see in this notation the idea of change in y over change in x. You see that? So a small change in y over a small change in x. So that's kind of where that notation, actually that's kind of the most revealing notation of any of these. Except this one's good, rate of change of f with respect to x. But this doesn't really capture what's going on. It's just a shorthand way to mean this. Okay? All right, so so this is just the generalized version of that. If one function, the value of one function is c times the value of the other function, then the rate of that first function is c times the rate of the second. Okay, so this is a generalized version of that example with John and Mary. John traveling a distance 5 times as much as Mary. So now we're just saying any quantity, if a certain quantity is always 5 times another quantity, then the rate at which that first one changes is always c times the rate at which the second one changes. So this is a closed form rule that we want to verify. Okay, I want to verify that. Again, we still read all of those as the rate of change of f with respect to x is c times the rate of change of g with respect to x. Okay, so we want to prove it. So, given this, we know this, can we prove that this is true? Okay, can we prove that this is true? And so that proof will be based on, what will it be based on? So let's just review this one style of proof. That's an important to know. Were you going to say something?
No.
Okay. All right, so that we're going to prove that A equals E. All right, so can we declare that fact? Can we state that fact? No, that's our conclusion, right? So it's kind of like we're pretending. So we know it is true, but we can't use it because the very thing we're trying to do is confirm it with all of the other information that we know. So we can start with A, and we say, oh, well, we know A equals, maybe by a definition or maybe by some algebra, okay? And B is the same as C, and we continue this process until we string together equalities to get Z, and the conclusion then is conclude A equals Z. Okay, so this is one type of proof, and it's in terms of these proving these closed form rules. It's an important type. Okay, so can we do it? So now, what are we trying to prove? So we've got, this is our given. And we're going to prove that the rate of change of f is c times the rate of change of g with respect to x. Yeah. Then, yeah. Hopefully you all caught that. My mind was on something else here. So how are we going to do it? If we're trying, we're trying to show that this equals this. So where do we start?
We just take the average, like, so you have what x plus h minus. You go there.
Okay, and why? What is that?
Well, that's the rate of change of f with respect to x, but that's the average rate. So
You're saying that this is what?
Is equal to g g of x plus h.
Oh no, you had it. You changed gears, Aaron. So what's our proof? So what are we trying to do? We're trying to show that A equals Z, right? So we start with A. And what do we do with A? We write what we know it's equal to. We write what we know it's equal to. Maybe that's a definition, maybe that's algebra. But do we know anything about R of f of the rate of change of f with respect to x relative to g?
No.
No, we don't know anything about this relative to g. So what do we know? So what does this equal? What do we know for sure? Nicholas?
F of x plus h minus f of x over h.
You see? A equals B. 100% confident of that, right? There's no doubt about it. That's our definition for the rate of change of f with respect to x. Okay, where can we go from there? So now we've got the function f involved, right? We got the function f involved. What can we do with this? So we want to be able to declare something that we confidently know is equal to this. Idea? Yeah. So what could we say this is equal to? Or maybe just start with this. What is f of x plus h equal to?
Is c, g, x, plus h.
This is what he wants. C, g, x plus h. Is it right? Just this first part right here. Agree? Not sure. That's a lot of blank stares. Do we know this is true for sure? So then what does f of a equal? What is f of a?
CG of a.
CG of a.
So that's true.
What about f of star?
CG.
CG of star. What about f of x plus h? C g of x plus h, right? Okay. F of x. C g of x. See, you can only write things down, write an equality that you're 100% confident of. We know what f of x plus h is from our given. It's c times g of x plus h. And we know what f of x is. It's c g of x. Okay, so now you kind of get going here, and we want to keep track of where we're trying to get to, right? We're trying to get, in the end, we want this all to equal what? C times the rate of g with respect to x. So now you start looking at this and saying, can I make it? How can I get from here to there? So I want to give you a minute to see if you can figure it out, see if you can do it. So we're going to continue this string of equality. Can I get from here to here? Okay, so we're here. Kyle, any idea what we can do with that? Gilbert,
I want to bring out the c to the front.
you want to bring out the c to the front. So I got c times. And why do you want to do that?
We could say that rg of x
Okay,
is equal to g x plus h minus g of x plus h minus g of x plus h.
okay, so what you said was this right here. Do you recognize what that is now? Do you recognize what that is?
It looks like
Brent?
This is just the average rate function again.
For which function?
G.
For g now. Do you see? So when you get to there, you recognize, oh, that's the rate of change of g with respect to x. So what does that thing equal? C times the rate of change of g with respect to x. We got it. We're done. See? So because A equals B equals C equals D equals F, therefore A equals F.
So we don't have to say like, oh, we take this in or like that. We just say zero.
How come we don't have to take the limit?
Oh, well, like we added the tax, so those are essentially equal. I mean, the g of x plus h minus g of x over h. That's essentially equal to r.
It goes back to the discussion, what I was pointing out at the beginning of class, that what does the rate of change, what does the rate of change of f with respect to x, that notation represent?
Exactly.
No, we're reserving it for the approximate rate, which could be exact if h was sufficiently small enough. It doesn't have to have the limit, or it doesn't. It doesn't have the limit. So that was what I was saying at the beginning. So if we're trying to prove that, and that doesn't require the limit as h goes to 0, then we never need the limit. Make sense? Questions on this proof? Okay, so we've got 3 rules now. The first rule was, I'll just jot them down, making our list. We had x to the n. And we showed that that was n, x to the n minus 1. And then we had the function was a constant function. Function whose accumulation, it never accumulates, either positive or negative. What's the rate? 0. Okay, and now we have a function who is a constant times another function. And what's the rate of change of f with respect to, f. So now our original function is some constant times a function. What's the rate of change This is kind of weird notation here because I'm calling this f. So say what should I do? So yeah, let's go back to this as being f. And I'll call this just something totally different like u, okay? So f of x equals c times u of x. So if a function is in the form c times another function, call it u, then what's the rate of change of f with respect to x? That's what we just proved. C times the rate of u with respect to x. So those are the three closed form rules we have so far. Closed form rules. Any questions? Okay, so let's have you practice. Same kind of idea. Can I erase what's up there? So here's just a nicer form. This is exactly what we did. We said that the rate of change of f with respect to x was our definition. And then we changed each of those using the given. We changed each of the function f to c times the corresponding g. Factored out the g, and that gave us c times the rate of change of g with respect to x. So that's a cleaner version. Okay, so I want you to do this. So if the rate, if a function k is the sum of two functions f and g, then what would be nice if for the rate of k to be? The rate of k with respect to x. What do you want it to be? Today you get your wish today. What do
Rate of f plus the rate of change.
he wants it to be the rate of change of f plus the rate of change of g. Okay? Oh, jeez. Okay, and that's what it is. So we're going to prove that the rate of change of k with respect to x is the rate of change of f with respect to x. So, given that the function in question is the sum of two other functions, prove that the rate of change of our original function is the sum of the rate of changes. This is for you to do, okay? Practice, go. This is how you start. You start with the rate of change of k with respect to x, and you know that it equals to its definition of the average rate function, right? The average rate function. You don't know anything about the rate of change of k with respect to x in terms of the other rates. All you know is what you know about where that rate of change function comes from. It comes from the k function, right? So now what is k of x plus h? So we'll go through each thing. What is k of x plus h?
F of x plus h plus g.
F of x plus h plus g of x plus h and k of x. It's just the definition, right? F of x plus g of x. Some of you were jumping to the conclusion too fast. You were jumping into the rate split up. But you got to do it one thing at a time. That k of x plus h is the sum of f and g at x plus h, and k of x is our original function definition. Now we take a look at this and say, okay, now how can I get the algebra going so I can end up here? What am I going to do? Peter.
You separate the R of f into the f of x plus h, and that whole thing into R of g into the same thing, and then add them together.
How are you going to do that? So how do you get them separate?
Well, you just have the f of x plus h plus f minus f of x over h.
Okay.
I get the quantity, then plus g of x plus h minus g of x over h.
Good. So you can kind of see this forming, right? We know that our rate of change of f with respect to x is going to be that minus that over h. We have it. And then our rate of change of g with respect to x is going to be g minus that over h. So it's just a matter of rearranging things.
We have to include that step there.
Oh, absolutely. Yeah, because you don't know anything about the rates of f and g from this statement.
So you have to, okay, so you're defining what, okay, I get it.
Yeah, you don't know anything about the rates of f and g from the statement. Okay? We know what this function, what k is in terms of f and g, and we know what this k is in terms of f and g. We don't know anything about the rates yet. You see?
You have to define it before you can.
Yeah, so, right. So now we switch things around and we get that f of x plus h and the minus f of x together. Okay, and so then that's how we split the fractions apart. It's like, you know, when you add fractions, you have a common denominator. Well, notice we're doing it, we're splitting them apart with a common denominator. And we got it. Questions? Anybody have a question?
For the,
Yeah, please.
The fourth step, how do you get from the third to the fourth? You just
Talking about this to this?
no,
This?
yeah. All you do is just distribute the negative and then just move it around.
Yeah, we just changed the order. So we got a minus f that we put second, and we got a minus g, we put that third, right? So plus g of x plus h, and then that third. And then just group them together. Other questions? Okay, so I think, question, yeah?
Check our work, we can do it in reverse, right? Should work.
Yeah, sure. All right, so here's some different notations for the same thing. The rate of change of k is equal to the rate of change of f plus the rate of change of g. So another way to say that is, since k is f plus g, we'd say the rate of change of f plus g. And then we can use our exact notation, but we still call it the same thing. This is still, what we say is the rate of change of k with respect to x equals the rate of change of f with respect to x plus the rate of change of g with respect to x. And this is the same thing again. The rate of change of k with respect to x equals the rate of change of f with respect to x plus the rate of change of g with respect to x. So we practice always using that language no matter which notation we're using. And we know that those last two, those are exact. And this could be exact if h is sufficiently small, then that first one is exact as well. Any questions? Okay, so here's our summary. We've got x to the n, we've got a constant function, we've got a function that's a constant multiple of another, and a function that's a sum of two functions. These are our four basic closed form rules. So x to the n, our rate of change is n x to the n minus 1. If the function is a constant, the rate of change of that function with respect to x is 0. If the rate of change is, or if the function is a constant multiple of another function, then the rate of change is that same constant multiple times the rate of change of the g function. And then the rate of change of k is the sum of the rate of change of f plus the sum plus the rate of change of g with respect to x. So we're going to practice here. So if you've done these before in a previous calculus course, I want you to slow down and just kind of erase this this pattern that you learned, and kind of slow down and take a look at how does this function embody all four types, okay? And so when we do derivatives, especially when they get harder, these closed forms, the first question we're always going to ask is, what's the overall structure of the function, okay? Because the overall structure of the function will govern then what rule we apply. Because we're actually going to apply all four rules to do this. We're going to apply all four rules to do this. So to get started, we have to know the overall structure to know what overall rule applies. So I want you to first ask, everyone think to yourself, 1, 2, 3, or 4, which of those four rules would apply to the overall structure of the function p? So think to yourself. So what we're asking is the overall structure something to x to a power of n? Is the overall structure a constant? Is the overall structure a constant times another function? Or is the overall structure the sum of functions? Everyone think they got their answer? Molly, what do you think?
I think it's sum of functions.
She thinks the overall structure is a sum of functions. Zoe, you agree with that?
I mean, there's also constants though, in front of them.
Okay, right. We're looking at the overall structure, the big picture. Caleb.
I was thinking the first one.
So this whole thing is x to raise to a power.
Oh, no. It's not.
No, what do you think? So what is this whole thing?
I guess you mean the last one.
The last one too, right?
I just want to say it seems like you can use them all.
But the overall structure, as the big picture of it, yes, we're going to use them all. But there's one of those that represents this function as a whole. And that's what we're asking.
It's got to be the sum of all.
Okay, y'all got it. It's the fourth one. It's the sum, right? Because this is the sum of functions. So what's the rate of change of p then? So the rate of change of p, applying that rule, is, for applying the rule of the sum of functions, what would it be?
P of x plus h, or,
We're going to apply the rules now, so we're not going to use definition, but so how can we represent what the rate of change of p with respect to x is, applying the rule that you all picked?
Are we just like putting them, are we separating them so we can see it, or?
Can we call each of them the different F, G, H?
Yeah, or we can just, instead of f, we can just have that.
Okay.
So,
So the
the rate of change of x to the 11th with respect to x, you see? Plus the rate of change of negative 5x to the 4th with respect to x. I'm not exactly getting them underneath, so you get the idea, but I want to start over. So the rate of change of x to the 11th with respect to x plus the rate of change of, make it so big, the rate of change of negative 5x to the 4th with respect to x plus the rate of change of 10x cubed with respect to x plus the rate of change of 9. So now we go to this first one. We look at this first one. What's the overall structure of that? Rule number 1, 2, 3, or 4? Rule number 1. What is the rate of change of x to the 11th with respect to x? 11x to the 10th. So your homework for Wednesday, you had some practice with these, right? What's the overall structure of negative 5x to the 4th? 1, 2, 3, or 4? 3. You see that? So it's, what will the rate of change be? It'll be the rate of change, it'll be negative 5 times the rate of change of x to the 4th, which is negative 5 times 4x cubed. That's rule 3. Do you see it? What about 10x cubed? 1, 2, 3, or 4? Rule 3. 10 times the rate of change of x cubed. 1, 2, 3, or 4? It's a constant, right? That's the rate of change of 9 with respect to x. That's not g, that's 9. So it's the rate of change of a constant with respect to x. Okay? So we could simplify here. Yeah, ask me.
So if, like, we were asking to prove from step 2 to step 3, where it says r to respect of, or the rate of change of negative 5x to the 4th with respect to x, that going down would actually be negative 5. And then we do that, do we actually have to write x to the 4th, or the rate of change of x to the 4th, or we just conclude
Yeah, so I skipped it. I mean, if we were explicitly writing on every single step, then that would be yes. It'd be -5 times the rate of change of x to the 4th with respect to x.
Okay.
But, so I just did it.
Okay.
Yeah, totally. Yeah. So you could have done one more intermediate step from there to there, and there to there. That's right. Any questions on that? Okay, so yeah.
So r 10x to the third of x, that rule would be like the third one, right?
That's the third one. And so what does that equal? That equals 10 times the rate of change of x cubed with respect to x, which is 10 times 3x squared. Yeah, so I did skip a step there. Okay, so now, with a little bit of practice, you'll be going right from here to here. But what I wanted to point out was when these derivative rules get more complicated, it's this train of thinking that's going to be able to allow you to do it. So on a polynomial, so we just, eventually just 11x to the 10th minus 20x cubed plus 30x squared plus 0. But it's this train of thought that's going to enable us to do harder ones. So I want to practice that to start. So how can we check that? So now in following these rules and doing getting closed form, we're following these rules, we're doing algebra, and we're prone to mistakes. Okay? So how can we check to see if our R of P, our rate of change of P with respect to X, is correct? How could we check that? So we don't necessarily always trust our algebra or our rule following skills. But what can we trust? What in graphing? So what about graphing calculator? So how can we use graphing calculator?
The original function and the rate of change function and see if they.
Which rate of change function? Yeah, good. So so we're saying that
Approximate rate of change function, right?
okay.
Yeah.
Is it approximate?
Because you used R. No, I guess we are at exact. I'm sorry. I was going to say that we could take the accumulation function and plot it, and then plot the approximate, and then shrink the change in x to see if it
Nice.
lines up.
Yeah. That's it. So let's just call the rate that we found h. Okay, so we'll do h of x, and this is what we found with the closed form rules that we've got so far. So what did we find? 11x to the 10th. Is that it? Plus 0. Okay, great. Okay, and so we want to graph that. And let's zoom out here so we can see more aspects of this. Oh, is it just open up upward like that?
Yeah, you might have to zoom in. Like, and those are just wider.
Okay, that's good. Let's zoom in a little bit. So we see it's asymmetric. That's something of interest, but not the most exciting function, but it's what we got. All right, so do we know for sure this is correct? No, it's based on our own algebra, right? And so we're pretty sure it was pretty easy. It was easy algebra, easy rules, but we want to know for sure. So what do we do? Ryan, what do you want to do?
You want to plot the original accumulation function.
Okay, the original accumulation function was, tell me,
I don't have that.
x to the 11th,
X to the 11th.
Minus 4x to the 4th.
or
Minus
5x to the 4th. You're fine?
plus 10x.
Plus 9.
Okay, so So you want to graph that? Is that what you want to do? Okay, there it is. So did we get our... So Shane is saying we don't want to graph that, we want to graph the rate of that. Yeah, because this is our accumulation and this is our rate, right? So instead of graphing P of X, what do you want to graph? R of P of X. Okay, well, we haven't told graphing calculator what R of P of X is. How are we going to do that? What's that? Tell me. Yeah. So, what is it? Okay. So you got it, but we want to get the right syntax. What do we want? So let's do F. So I'm going to do F of. So this is right, but it won't work. Why not? What do we need to change? What's that? We want F or P? We want P, right? So I call it P. So or we could call this F. How about we call this F? Make it easier. Is that okay?
Yeah.
There we go. All right, so I just changed RP to F. And so is this going to do it? Do we need anything else? What's that?
I don't know where there's needed, we have to use RX now. Let's say y equals R6.
Okay, y equals R of X. Is that going to do it? Why not? What is H right now? So H is 1. What do we think about that? Is that going to... You want to just try it? Let's just try it. So now I'm graphing our original function, the rate that we found using the algebra of the rules in red, and now I'm graphing the rate function in blue. So did we get it wrong?
No.
What's wrong? So
Isn't the constant what's messing it up? It's shifting it.
constant is shifting it.
Because remember, we have 9 in the accumulation function. And that becomes 0, so is that shifting the graph?
No, that's not the problem, because if that's the rate comes, you're comparing a rate to accumulation.
Oh.
So the rate won't have a 9 in it, and that's not going to... What's wrong? What's wrong?
I'm not sure.
Okay.
That, we have an exact one, I guess we're closer to an approximation, maybe with H of X.
Which is exact and which is approximate? H of X is exact?
Yeah, and then R of X is approximate. And but we're setting R of X as our H as our set of 1, which should be 0 if we want it to be like 0.
Okay, right.
Do we need to put a limit in with our rate?
Okay, or we could just do it.
Right now it's an approximate.
I should have called this something different. Sorry, this is confusing. So this H is different than the name of this function, right? So I'm going to go back and call our derivative G, so there's no confusion there. Okay, so the name of the rate function we found G now is something totally different than H. So what about H? Yeah, like what?
0.
What about 0? It's going to work?
Oh.
No. The whole point is we need sufficiently small, but 0 is going to make the rate undefined, right?
Like 0, 0, 1.
Ready? Did it.
Is there another way of checking?
Maybe, but we like this way. So,
Can you just take the integral and see if it matches your accumulation function?
okay. Okay, so as you walk out, so here's h equals 1, and if you let h get sufficiently small, then our open form rate shows us that the, maybe?
If you put a limit in that rate, it makes it.
We're doing the idea of limit.
I'm just trying to tie those two ideas together. So,
Yeah, but you, That's doing a limit.
That's what I'm trying to say. That it's an approximate because we're not defining what age is.
if you don't define what h is, then it'll make it 1. The default is 1.
Okay. But once we define it, then it'll start.
But now make h sufficiently small. You got it.
Want to keep it?
No.
Yeah, I just need to.
James, do a second.
Have a good weekend.
Is there any other issue besides the circle thing? Okay. So you could have just picked one. You just did it. But it's okay. Yeah, it's fine.